Okay, so here's an application problem modeling vertical motion. So imagine a rock being launched straight up into the air. It's going to reach a certain height, and it's modeled by this S equation, which is measured in feet after t seconds. So I have a little illustration here where we're just showing that a rock is going up and then it's coming straight back down and then hitting the ground. So the first question is, how high does the rock go? So we're looking to find really the maximum height. Okay? So knowing that's what we need, let's think about what a sign diagram would look like for velocity. So just understanding this concept, we know that we can't have negative time, and at some point in the middle it's going to reach its high point. Now on the way up it is moving away from where it started. It's moving forward, so to speak, so we know that would indicate a positive velocity, and on the way down the velocity would be negative. So that's just showing us the direction of the movement. Okay, so again, this positive is indicating it's going up, this negative it's going down. Okay, so where the sign changes, we know the velocity is going to have to equal 0. So we're after the time value when that happens. So we need to find our velocity, and we need to set it equal to 0 and solve. Okay, so we need to solve this equation, okay, to find the maximum height. It's going to occur when the velocity is equal to 0. So it's not going up anymore, it's not going down, it's temporarily at rest. So if we find our velocity equation, recall that the velocity is the derivative of our position function. So our derivative is going to be 160 minus 32t. From there we're going to set it equal to 0 and solve, and we get t equals 5. So we can come over here now, and when we are 5 seconds into this rock's path, 5 seconds into this so-called trip through the air, it's going to reach its high point. But now we have to be careful. The final answer is not t equals 5. The question says, how high does it reach? So we need to find s of 5, which gives us the position. So when we do that, when we do our substitution into our position function, or our height function, we're going to get 400 feet. So that would be the answer to the question. Okay, in our next problem here, we're looking to find the velocity and the speed when the rock achieves a height of 256 feet. Okay, so before we can find our velocity and speed, we need to determine the time value when this occurs. So we need to take our s of t equation and set it equal to 256, since we know that the height is 256. So make your substitution and then solve for t. So when we do the algebra here, I'm getting everything over to one side so it's equal to 0, and then we can pull out a 16 and we can factor this quite nicely. We end up getting t equals 8 and t equals 2. But we want the velocity and the speed when that happens. So first we need to find the velocity at each of these points. Okay, so now we're going to plug into our velocity equation from up above. So when we do our substitution for v of t, so this is when it's on its way up, we have 96 feet per second, and for v of 8, negative 96. So obviously, well, hopefully it's obvious, maybe it's not, but the positive velocity indicates it was directed upward, right? It was moving upward, and the negative velocity means it was on its way back down. Now, if we also want to find the speed we know is the absolute value of that, so this would be 96 feet per second. Okay, in our last question, we want to know when, so we're talking about what are the time values. When is the rock speeding up and when is it slowing down? Well, recall we said our velocity equation was that, and we need acceleration. Well, that's going to be negative 32, And if we're talking about acceleration, this is going to be measured in feet per second squared. Okay? So, what we need to know if we're talking about speeding up and slowing down, we need to get a feel for what the signs are. So, to do that, let's make a couple sign diagrams. The first one for velocity and the second one for acceleration. Alright, so if we take a look at our sign diagrams here, we said earlier we know that the particle is changing directions when t is 5. It's heading upward and then it's heading downward, so the velocity tracks the direction for us. And acceleration is always going to be negative because we can see that it's a constant negative 32 feet per second squared. So it's speeding up when our signs are the same. And our signs are going to be the same for t values greater than 5. That's where they'll both be negative. Slowing down, well, that's going to happen when the rock is on its way up. So between 0 and 5, it's going to be slowing down. Think of it as it's battling against gravity. On the way down, it's going to be, after 5 seconds, it's going to be speeding up because it has gravity on its side. Okay, it's falling, and again, we can see that indicated by the signs being the same. It's also interesting to take a look at the graph of all three of these graphed at once. So I've graphed our s function in black, I have the velocity in red, and then I have the acceleration in green. And at this point right here, this is where t is 5. So you can see on my s graph, we have a maximum height there. And you could also see in my velocity graph, it's where it's equal to 0. And also notice that my a graph, this is the negative 32. It's a horizontal line, right? Would have a 0 slope. So that's kind of helping you put those pieces together and hopefully get a feel for what those three graphs would look like.